Lesson 2, Structure Models. Now we're going to go into a bit more detail on each model, first starting with the structure model. In this lesson, we will consider components and substances, connection types, and connection directionality, properties and values, and quantitative versus qualitative values. Recall that structure models contain components and substances, the connections among them, and their properties and values. All systems are comprised of the structural elements, components, and substances. These are what makes up a system. We represent these as dark and light blue boxes in our models. For now, we can think of components as the discrete parts and subparts of a system. For example, components in a simple flashlight, which includes a little more than our light bulb circuit, might include the batteries, wires, casing, light bulb, and on-off switch. A light bulb may also have subparts such as housing, interface, and filament. We can think of substances as things that move through a system. Substances are of three basic types: energy, information, and material. Material might be liquid, like water, solids, or gases. Signals are a kind of information. And in the case of our flashlight example, electricity and light are kinds of energy. Substances can be liquids, gases, solid materials, energy, or information, each of which can move through a system. Structural elements within a system are connected to each other via structural connections, which enable their interaction. In other words, a structure can only interact with the structural elements to which it's connected. Let's take the example of two components, circle and square. As they stand, they are not connected. But what if square was inside circle, like so? We say square is contained in circle. That is, square has a contained-in relationship with circle. We see the connection type is contained in, and the arrow points from square to circle to indicate that it is square that is contained in circle. Now, what if instead the square and the circle were attached like so? That is, square has an attached connection with circle. In this case, circle is also attached to square. This is a two-way relationship, so the arrows point in both directions. Finally, let's say that circle rests on square like so. We say that circle has a rests-on connection with square, and again note the direction of the arrow tells us that it is circle that rests on square. There is nothing special about the connection types contained in, attached, or rests on. There are as many connection types as there are ways of connecting two different structure elements. Once again, for our light bulb circuit, we see the attached connections between the battery and switch, between the switch and light bulb, and between the light bulb and battery. We also see the contained-in connection between the substance electricity and the component battery. Here we want to make two important points. First, that by convention, the structure model details the connections amongst components at the initial state. Second, is that changes may occur to those connections over time, for instance, as electricity moves from the battery to the light. Generally, we do not create more than the initial structure model. Instead, we infer future structure models from a combination of the initial structure model and the behavior model, which will detail the changes to the model over time. Structural elements each have properties that help describe them. For example, a light bulb may be described by number of watts and interface type, a battery might have voltage, and a switch might have a mode. Water might be described in terms of temperature, salinity, etc. For our models here, we will represent properties as green boxes below their corresponding structural element. Furthermore, the properties of structural elements can, and usually do, have values associated with them. A light bulb might be a 10 watt, 50 watt, or 100 watt bulb, for example. Likewise, a plug might have 2 or 3 prongs, and water might be very salty or not salty at all. Values in our models will be placed in the same box as the property to which it corresponds, separated by a colon. Each of these properties may take on a decimal value. For instance, temperature equals 94.7 degrees. An integer, for instance, might have a number of plug prongs equals 3, or what we call descriptive values. For instance, connection type equals screw in, or mode equals off. We're used to seeing quantitative values associated with properties, such as temperature equals 94.7 degrees. A quantitative value is simply a numeric value associated with a property. However, often in SBF models, you will see qualitative values such as hot, fast, high, etc. In fact, people often use such qualitative descriptions for common sense reasoning. As I write this, I know it is hot outside. It may be 95 degrees, or 97, or 94.2. For my purpose, it doesn't matter. I know to not spend too much time outside exercising, to dress lightly, and generally that I should drink more water. Hot is a qualitative description that I can use to make inferences and draw conclusions. Note, hot is also relative. I'm also drinking a cup of coffee at the moment. If my coffee was 95 degrees, I consider it lukewarm and probably not very good. For coffee, hot means that it might burn my mouth, so I should sip it lightly until I know that it won't. I don't know the quantitative value for hot coffee, but I do know it's something less than 210 degrees, or it would be boiling. Qualitative descriptions can only be understood in the context in which they are described, or, in our case, in the SBF model in which they are used. The downside of this is that hot in one model might mean a different temperature than hot in another model. Now let's revisit the structure model of the light bulb circuit. Again, notice that components are blue, substances are light blue, and connections are indicated by arrows with annotations in teal. We describe some properties and values associated with each component, such as the location of the electricity, how many watts the light bulb takes, and the voltage of the battery. Also note the mode property of the switch and its value off. Think of a very complex system, for instance, a car engine. The car engine has many moving parts all working in concert to achieve the function of making the car move. If we look at a car engine working, we see a blur of motion. Now, imagine yourself taking a picture of that car engine as it works. A state is like that picture of that blur of moving parts. When we take the snapshot, we can see where each of those moving parts are at that instant in time. A state describes the properties, values, and connections of the structural elements of a system at a given point in time. We can think of the structure model, then, as a complete description of the initial state of a system. We'll see this concept of the state of a system used much more for both function models and behavior models. To review, structural elements are either components, which are discrete parts, or substances which can flow through a system. These are the what of a system. Structures have properties like size and temperature, and properties take on different values like 22 degrees Fahrenheit. These are the important characteristics of the structural elements of a system and can take on either quantitative values, such as 94.7 Fahrenheit, or qualitative values, such as hot. Structures are connected to each other via structural connections. These are the physical relationships between structural elements in the system. A snapshot in time of a system is a state, which captures the values of its properties at that point in time. A system can have many different states.